Yeah, thanks Sheldon, and good afternoon everyone. Pleasure to be in Newcastle and presenting at this conference. So simulation in mining, what is it and why does it matter? When we talk about simulation, we're talking about a single digital representation, physics accurate, of a real world structural system. Be it a blast furnace, jet engine, heavy plant of machinery, we're talking about the fastest way to know if a product works without actually building the thing. For those of you that are unfamiliar or new to simulation, we sit as the middleman between CAD and CAM, or CAD and physical testing. CAD represents what the product will look like, but CAD alone doesn't tell us whether the design is going to work. And CAM, it builds the product, but CAM alone only translates the product into manufacturing steps. So simulation is sort of the bridge between what looks good in CAD and what actually works in reality, ready to be manufactured. Again, for those new to simulation, it involves taking your CAD, taking your geometry, generating a mesh and defining your physics. So these are things like your operating conditions, your material properties and your loads, and then being able to solve the model to predict how your product, how your system, how your structure is going to behave in the real world. But what does this all look like, and how is it applicable for today's discussion, and how have customers and how have companies in this industry utilised simulation to make a real difference? Well, just quickly, we've worked with Austex to validate their structural designs, and this includes their drill rig equipment, their platforms, lifting equipment and rig steelwork. Hatch have used our discrete element modelling solver Ansys Rocky, and they use this to understand how transported material interacted with their belts and their skirts, and whether the design created any jamming risks. So Alcoa have been using CFD simulations for the better part of, say, 20 to 30 years now, obviously starting back then with small-scale 2D simulations, and now progressing to large dynamic 3D simulations. And in this design here, you can see them running through over 100 different design scenarios to optimise the design of their equipment. And recently, TimeStep have used our explicit dynamics tool, LS-Dyna, to analyse a rhombin experiencing severe deformation and high-risk fatigue cracking. And through simulation, they were both able to identify the root cause and find a reinforcement strategy that was able to extend the service life of the bin by about 2 years. So one of the earliest applications of simulation in the mining industry, and probably still the most applicable for today's discussion, is Ansys Rocky. And you see here, this is Ansys's flagship discrete element modelling solver. And what Rocky enables us to do is simulate the behaviour of particles and bulk materials, where we are looking at how particles behave and interact. This is both at a particle and particle level, and also at a particle and boundary level. And by doing this and by capturing these interactions, what Rocky allows us to do is analyse the complex behaviours between the granular and bulk materials that would be both difficult, very expensive, or otherwise impossible to measure physically. And we're able to open up questions and address questions surrounding material flow and handling, efficiency and throughput, loads and stress management, and equipment wear. So again, where has this been used, and where has this been used locally? On the screen here you can see an example with Tundra bulk solids, and they use discrete element modelling solver in Rocky to analyse the performance of a truck unloading station handling dry, loose limestone. And why do they do this? They were looking at understanding the interactions and how different unloading positions and the Grizzly designs, the great designs you can see there, to evaluate the critical particle velocities to predict where the breakage was most likely to occur, and understand how this changed equipment wear over a different life span. So as a result there, you can see in the bottom left of your screen there, we were able to reduce degradation by about 25% and material accumulation on the Grizzly or Great design by 40%. And you can see that indicated by the different line types there, the black, green and blue, with the preferred blue line being one that had less material accumulation. So maybe what comes to mind more when we talk about simulation is the fancy term computational fluid dynamics, or CFD. But here we're looking at the core physics of flow, heat transfer, turbulence, mixing, multi-phase behaviour, and simply put, we're just looking at predicting how fluids and gases behave in real operating conditions and allowing us to visualise what cannot be seen in physical testing. So this lets us dive deeper into understanding where pressure losses occur, where heat builds up, how gases flow, how slurries separate, and how dust disperses in a plant. So again, another example, nice and close to home, looking at a recent project with Ampcontrol. CFD analysis was used to understand a transformer's surface temperature and then indicate whether the enclosure's temperature exceeded a hard limit of 140 degrees in this operating mine shaft. So yes, although it's intuitive to know that cool zones will correspond where the air from the cooling pipes will hit the walls and the enclosures, and vice versa, hot zones will correspond where there is little to no airflow. It takes complex steady state and transient CFD simulations to understand the temperature at these locations in typical operating conditions. And as a direct result, we were able to find with Ampcontrol that high temperature zones were concentrated at the centre of the enclosure, where there is little volume for the nitrogen to exert natural convection, and at the contact regions between the frame and the enclosure, where there was little air to reach. So with CFD and with Fluent, the tool used here, Ampcontrol were able to both quantify the temperature of the enclosure across the various design iterations. So we're looking at a flat lid enclosure, we're looking at a slope lid enclosure, and then quantify that temperature to find the most cost-effective and temperature-effective solution. This just helped reinforce their design decisions and their technical ability for their enclosure designs. This is an exercise that would be almost impossible to do so, or very expensive to do so in an operating mine shaft. So when we want to tackle simulations involving material failure and deformation problems, we have to sidestep into LS-DYNA. And this is where we address uncertainties in vehicle crashes, blasts, heavy impacts, occupant safety, and we're looking to understand the response of materials due to short periods of severe loading. And this is ANSYS's one code strategy, including most of our common solvers, so what we've talked before with finite element modelling and discrete element modelling, and we're looking to answer questions surrounding: will this structure survive a dynamic event? Where will failure initiate, and where and when will that be? And what happens beyond the elastic range? Or, more specifically, what speeds can our safety barriers safely redirect our heavy mining equipment? And this is a question that the University of Newcastle were able to answer on behalf of Bengalla Mining. A great example here of including most of the common solvers in LS-DYNA to address some key questions. And the challenge here was to model the impact between the heavy mining equipment, the vehicles, and the roadside safety barriers, and then understand the most suitable, cost-effective, practical solution to protect both the driver and equipment during collisions on haul roads. And what Dr. Klaus and his team were able to do at the University of Newcastle is use LS-DYNA to run a high-fidelity, explicit dynamic simulation. So the biggest takeaway from this project in my mind isn't just the quantifiable. It isn't just the influence that you could have on speed limits on these haul roads for safety. It isn't just the optimization of the road barrier designs or the increase in safety, but it's the benefit of repeatability. Repeatability for different site conditions and repeatability at any given locations for any type of design, doing this without actually running any physical tests. So although it may seem very obvious, and most of you today will know this, that the sheer scale of heavy mining equipment and the subsequent cost of this physical tests, it's a major bottleneck in design reiteration, in that rapid design approach. And simulation is able to open the door in many different ways to model, test, and predict how such systems are going to react and behave. So a quick word on who we are at Leap Australia and how we fit into all of this. At Leap, we are the channel partner for Ansys simulation software in Australia and New Zealand, and alongside what I presented today with structural analysis and CFD, we have a strong history in software solutions, everything from digital twins, optics, electromagnetics, and much, much more. So if any of this has sparked an idea or question of yours, please feel free to reach out to myself, Matei and Angelo sitting back there, or floating around for the rest of today's event. Thank you very much.